Okay, thank you very much. So thank you very much for the introduction and for the opportunity to present our results. So I'm Filip. I'm a postdoc at the University of Chicago in the group of Liang Zhang. And I'm going to present our recent results on quantum repeaters based on concatenated bosonic and discrete variable quantum codes. So our work is available on arXiv, and this work was done jointly with Kongju, who is now a researcher at the Amazon Web Services, Shan Xu and Liang Zhang, who are at the University of Chicago, and Saikat Guha at the University of Arizona. So we have already heard a lot today about these two-way repeaters based on heralded entanglement generation with a possibility to include a heralded entanglement purification. But we have also heard about this limitation that the repeater nodes need to constantly wait for this heralding information, whether this heralded entanglement generation was successful or whether this heralded entanglement purification was successful. And if we try to scale up these networks, that will start making such networks slow, and will also impose non-scalable requirement on the quality of the storage in quantum memories, because they will need to be able to store this state for longer and longer to make sure that the state is there while we wait for this communication message. So an alternative type of repeater, an alternative strategy has been proposed based on error correction. So these so-called one-way quantum repeaters, where the idea is that we make most of these components near deterministic. So specifically, we would say that the sender encodes the logical qubit redundantly in some large number of physical systems, large number of qubits, in some loss-tolerant codes, such that when all these physical qubits are transmitted through the channel, the next repeater can decode and retrieve the encoded information, even if some of these physical qubits get lost. So the idea is that this repeater should be able to retrieve that information near deterministically, correct the errors, and re-encode for further transmission. And such repeaters are expected to be faster because all this information, all these processes are done locally without the need to wait for any additional information from anywhere else in the network or in the repeater chain. The challenge with this type of repeaters is the fact that these encodings for this photon loss-tolerant encodings is often to be quite large, and often we need to entangle together more than hundreds qubits in order to be able to overcome these losses. And that might also mean that in a repeater, then we might need to store all these qubits while we perform these operations. And so I understand in the next talk, Johannes will describe one possible solution to that with a specific implementation. But here we take a kind of a different route where we make the use of the fact that the pure loss channel that describes the optical fiber is a bosonic channel. So so what does it mean? So that means that our channel is in infinite, the space, this bosonic space is infinite dimensional. So that we can see by the fact that for this continuous variable space, that this mode carries the basis, if we express it in terms of the Fock basis of photon number, ranges all the way from vacuum to infinite photon number. So we don't need to encode the state in this two-dimensional qubit space. We can make a better use of each of such modes by encoding the information in this infinite dimensional space of that mode. And so how can we do this? Well, we can do this using bosonic error correcting codes. So bosonic error correcting codes would then encode the qubit in this infinite dimensional space of that mode. And so in this case, what we will do is we will basically replace each of those physical qubits in this picture with a qubit that is already encoded in that infinite dimensional space of that mode. And the specific bosonic code that we will consider here is the GKP code, where the GKP stands for Gottesman, Kitaev, and Preskill, and that was a code that was introduced in 2001. And so effectively what we will then have is we will have an encoding that consists of two levels, because on the first level, we will encode the qubit in each mode in such a continuous variable code. And then similarly as in this discrete variable encoding, multiple of such GKP qubits will be entangled together to form code words on the higher level. So on the first level, we'll have the GKP code, and then we will have a small discrete variable code on the higher level. So now I will provide some introduction and some intuition how this GKP code works and how we can use it to protect the information against the photon loss errors. So this GKP code arises out of the observation that while position and momentum do not commute and so cannot be measured simultaneously, we can actually define these two operators that are effectively periodic functions of position and momentum. And these two operators do commute, so we can measure them simultaneously. And measuring these two operators amounts to measuring position and momentum modulo root pi. And so this two-dimensional space stabilized by these two operators enables us to encode a qubit. And so, for example, a logical zero such as GKP encoding will be a superposition of position eigenstates separated by 2 root pi, and similarly the logical one, where the logical one will be shifted relative to logical zero, and that we can also see on this picture. While, for example, the eigenstates of the x basis would then be a superposition of eigenstates of momentum. And if we now want to visualize this state in the QP phase space, so here we present the Wigner function of such a GKP qubit, then we see that this corresponds to this kind of grid-like structure in this phase space. And the blue regions show the Wigner function negativity. So this effective state is highly non-classical. So now I will describe how this code can protect us against certain errors. So if we assume that at this black circles here, these are these peaks of this encoding. So this is the grid with this Dirac delta peaks and these black dots. Then let's say that our random displays, that we have a channel that randomly shifts this whole grid, for example, towards that green cross like this. So then, because measuring the stabilizers enables us to measure this position and momentum within this grid structure. So that means that we will be able to detect this shift and correct it back to the starting point. And the problem will happen if the shift is very large. So let's say that this peak that was here was shifted all the way up to here, which is beyond the size of our grid. So if the whole structure shifts like this, then we have a problem, because we will effectively think that it was only the small shift that happened. So that specific shift to here, we will only correct up to here, resulting in an effective shift by this root pi, which is a Pauli Z error in this case. And if the same happens along the other axis, that would be the Pauli X error. So we see that small displacements can be corrected and large displacements can lead to logical errors. So the next step is the fact that I describe how to use that code against this kind of Gaussian random displacement error that shifts the structure in the phase space. But of course, the pure loss channel when sending through optical fiber is not such a random displacement, but is energy attenuation. So everything gets shrunk and shifted towards the origin. But we can follow a specific strategy where after our loss, which attenuates the signal, we apply amplification to bring it back to the original position. And then amplification would effectively contribute noise, such that effective action of this loss plus amplification will result in this random displacement that I have now described. This GKP codes can correct quite well. So the second important part is that these Dirac delta functions are, of course, unphysical. We can only achieve them in the limit of infinite amount of squeezing. So in the realistic amount of squeezing, these peaks will not be Dirac delta peaks, but will be some Gaussian peaks that have certain width. And the sigma GKP here, the width of that peak will effectively quantify the amount of squeezing. So the more squeezing we have, the higher the quality of the state, and the closer to the Dirac delta peaks this Gaussian peaks will be. Okay, so I have described this GKP code and how it can protect us against photon loss errors, and now we'll introduce how we can concatenate it with a higher level qubit code. So the advantage of this GKP encoding is what we may refer to as analog information. So let us consider that we had this Dirac delta peak at value 0, and then we had effective random displacement channel that shifted our peak according to this distribution marked here by this Gaussian curve. And let's say that, so because of our stabilizer measurements that only enable us to measure each of these quadrature values modulo root pi, we can actually only obtain a measurement value between minus root pi over 2 and plus root pi over 2. So anything that actually is here will be kind of periodically mapped to this interval, and the same everything that would here would also be mapped to this interval under our stabilizer measurement. And let's say that we measured the value here, very close to the origin, to the Dirac, the delta peak at 0. So then we have multiple possibilities. The real displacement, the real error could have been either the small displacement to here, or a very large displacement all the way to here, or all the way to here. But because of this Gaussian probability distribution, we see that the probability that we misidentify the error, that we are going to correct this error, but the actual error was all the way to here, all the way to here, is negligible, because the probability amplitude here and here is very small comparing to this value. So we will assume with dominant probability that this is the error that happened, and the probability that we will make a mistake is very small. However, if we measure the value very close to this kind of boundary of our interval, then our error correction will be less reliable, because now there could be a possibility that either the shift was indeed up to here and we should shift it back to the left by this value close to root pi over 2, or the shift was actually all the way up to here, all the way to here. And now the difference in magnitude between this arrow and this arrow is not that large, and so the reliability of our error correction procedure would be smaller. So the interesting thing is that the value that we measure here not only enables us to correct the error or tells us what we should do to correct the error, but also provides us information how reliable our error correction was and what is the probability that we failed to correct the error. And this information we can use in the higher level encoding. So now let us consider a simple error detection code, a 412 code, which encodes a single logical qubit in 4 physical qubits with the following stabilizer generators. And let's consider the scenario where we encode our information in this concatenated code. So we will take 4 GKP qubits and we will entangle them together to form code words of this 412 code. And then we will send these 4 GKP qubits through this noisy channel. And at the end, we want to do GKP correction, and after that, the correction on this higher level. So as I mentioned, this GKP correction will provide us this analog information that tells us how reliable the correction was on each of these qubits. And that information we can use on the higher level. As an example, let's say on the higher level, we measure the stabilizer Z1, Z2. And on its own, if we measure the value to be -1, we know that that means that there must have been an error on qubit 1 or qubit 2, but we don't know on which one. But now we can use this analog information, which will tell us on which of these 2 qubits the GKP correction was less reliable. And that will be the qubit on which probably the actual error on the higher level happened. And that would be the qubit which we will correct on this higher level. And so we find that in such a concatenation of this GKP code with the 412 code, we can probabilistically correct most of single qubit errors and even some 2 qubit errors. In the second scenario, we consider concatenation with the 713 STIN code. So this is a code that will encode a single logical qubit in 7 physical qubits. And we perform exactly the same procedure. And then we find that now such a concatenation can probabilistically correct both single and 2 qubit errors, and possibly even some higher order errors, while on its own, the 713 code can only correct single qubit errors. So we see that the concatenation of GKP code with this higher level code provides this kind of boost to performance of the higher level code. Okay, so now I'm ready to present kind of our repeater architecture, which we can visualize as follows. So here, here in this inset, I provide the kind of the Wigner function of the single mode GKP encoded qubit. And these blue repeaters, they will effectively catch the GKP qubits from the communication channel and correct the errors that arose on those qubits and send it for the subsequent transmission. However, from time to time, the error will be so large that this GKP repeater, this blue GKP repeater fails to correct the error, resulting in a logical error, which is marked here by this red GKP mode. And that we can overcome precisely by the second level of encoding. So actually multiple of such GKP qubits will be entangled together to form these code words on the higher level. And from time to time, we propose to place these green multi-qubit repeaters that are more powerful and will will wait until all such GKP qubits arrive from a single encoding, and then we'll be able to operate collectively on all of them to correct this higher level error that the GKP repeater failed to correct. So now I'll briefly describe like the performance of this scheme. So in particular, we measured here the performance in achievable distances that we can achieve, for which the secret key stays above 0.01, the secret key per optical mode. And this value we can also compare with the capacity of the pure loss channel. So the optimal rate that we can achieve with direct transmission with perfect devices. So direct transmission here means without quantum repeaters. And it turns out that in that case, the secret key stays above 0.01 up to around 109 kilometers. Okay, so what is the performance of our scheme? So we consider three scenarios. The one scenario where we use only the GKP encoding, then where we concatenate this GKP encoding with this 412 code and with the 713 code. And we vary two parameters. One is the coupling efficiency, so the probability of successfully transmitting the state between the fiber and the repeater, and this amount of GKP squeezing that I described. So we give it here in the value of the sigma GKP, as well as in decibels, as I mentioned before. And so we see that if we consider only this GKP encoding, then for most of these parameters, we cannot achieve the communication of even 100 kilometers. But if we start concatenating, we can do much better. So with the 412 code, there is already a significant parameter regime where we can communicate over distances larger or close to 1,000 kilometers. And for the 713 concatenation scenario, for most distances, we can already achieve more than 1,000 kilometers, and for some of them, even close to 10,000 kilometers. So we see that this concatenation is a very powerful way of increasing performance with increasing the size of the higher level encoding just a little bit. And the second aspect that I want to mention is optimizing the resources or the resource cost. So the previous slide showed just the performance, but now let's say that we also define some kind of cost of this repeater. So let's say we define a cost function where in the numerator we will place the cost of repeaters and the denominator the performance. So the secret key per optical mode that we achieve. And now, so how do we define repeater cost? So we define it by the number of storage modes that are needed in each repeater to store this GKP data modes, as well as ancilla modes used for error correction, times the required storage time for this mode. So the time we need to coherently store this GKP qubits. And then the goal would be to minimize this cost function for all distances. And so it's clear that because this GKP repeater operates only on single modes and has much simpler operations, so it would be generally very cheap, while these multi-qubit repeaters will be more expensive. So here I show the optimal repeater placement configuration that minimizes the cost function for some specific set of parameters. So this is for the 412 code, this is for the 713 code. And so we plot the number of repeaters that we should place per 10-kilometer distance divided by the total, sorry, on the y-axis, while the x-axis we plot the total communication distance. And we have three curves. So the green and the blue curve corresponds to this hybrid architecture with two repeater types, where the green curve, this tells us how many of these more powerful multi-qubit repeaters we need to place, and the blue curve, how many of these cheap GKP repeaters we should place. And then for comparison, we also plot the number of these multi-qubit repeaters that we should place if we were to only use these multi-qubit repeaters, or only these more powerful repeaters. And then what we see here is that by going from this only multi-qubit architecture to the hybrid architecture that has two repeater types, we actually significantly lower the number of needed multi-qubit repeaters. So the green line is for most distances, and here for all distances below the red line. So we see that we can save on the powerful multi-qubit repeaters by adding this cheaper GKP repeaters, of which we need to place quite densely, but they are very cheap relative to these multi-qubit repeaters. And so finally, what would be the effective total cost? So there I describe the placement that minimizes the cost function, and what is the actual value of the cost function for these different schemes. So here we plot these 4 scenarios: the scenario with the 4-1-2 concatenation for the hybrid scheme and the scheme that uses only this multi-qubit repeaters, and the hybrid scheme and the one that uses only multi-qubit repeaters for the 7-1-3 code. And so the first thing that we see is that hybrid repeaters always allow us to save resources. So that we see, for example, by the fact that the blue line remains below the red line for the 4-1-2 encodings, and the yellow line, the hybrid architecture for the 7-1-3 code, remains below the purple line. So that's the first observation. And the second observation is that we see that if we want to minimize the cost function over all these architectures, that somewhere up to around 2,500 kilometers, it would be the best to use this hybrid architecture based on the 4-1-2 code. And for these distances from 2,500 kilometers to further to 10,000 kilometers, we should actually use the hybrid architecture based on the 7-1-3 code, because that would be the cheaper one. Okay, so to conclude, have shown that this kind of architecture where we concatenate the bosonic and discrete variable codes offers possibility of long distance quantum communication using only very small encodings on the higher level. So by small here, I mean 4 or 7 GKP qubits are sufficient for this higher level encoding. And then I have shown that the crucial features of our scheme that allow able to achieve this a good cost efficiency trade-off are this analog information and the fact that we can use 2 types of repeaters in a single architecture. So thank you very much. This is the archive number of our work, and I would also like to relate and refer everyone to a related work that also examines the possibility of quantum communication and quantum repeaters using GKP qubits, and this work in particular also focuses on using different encoding and decoding strategy to combat photon loss in such repeater architectures. Thank you very much.